Okay. So, quickly, homework, I wanted to cover it a little bit formally. Well, a few announcements. So I'll be posting homework 2 solutions right away. I'll post the quiz solutions right after class as well. I have a practice exam posted, and the practice exam solutions are also posted, so I would not recommend looking at the solutions until you sit down and try and take the exam by itself. The exam is 1 week from today, so we'll have office hours on Tuesday, and depending how it goes, we can maybe have a short office hours on Thursday for any last minute exam questions, maybe just like an hour or something or so. Chinmay is not in, so he will not be available on Wednesday, but I'll always be accessible by email. So, on the homework, we are going to take the van der Waals equation of state, and we are going to use it to calculate a plethora of properties. What you've done so far is you've used this to calculate the vapor pressure at one temperature, right? And for those of you who actually looked up the real vapor pressure of ammonia at 0 degrees C, the van der Waals was significantly off. It's not particularly good. What we're going to expand on this is, so for last homework you calculated at one temperature. Now we're going to calculate it as a function of temperature over a fairly wide range. We're going to use this information to then calculate the heat of vaporization, the entropy change of vaporization, and the volumes of the liquid and volumes of the vapor. Then we're going to further calculate the the internal energy of the liquid, the internal energy of the vapor, the enthalpy of the liquid, the enthalpy of the vapor, the entropy of the liquid, the entropy of the vapor. So the end result is basically, the easiest way to visualize this is a lot of plots. So the plots that I'm asking you to produce, one is a PV plot, and this is where we be figuring out, visualizing kind of the phase diagram here. And it should look something like this, where here is the critical point, here's the liquid properties, here's the vapor properties. In addition, you'll also be generating another plot. The shape, don't worry about the shape too much. The general trends is what we're going to be caring about. So for the heat of vaporization and the entropy of vaporization, right, they're all going to start off at some finite value. And then eventually, at the critical point, what should all of these values be? 0. So it ends up something like this, kind of. Now for the internal energy, the enthalpy, and the entropy, so we're going to be plotting on different plots. I think I got to double check, make sure I made it clear. I'm looking for 3 different plots: a plot for U, a plot for H, and a plot for S. But in each of them, we're going to have the liquid and vapor, liquid and vapor, liquid and vapor. So your final result that you should be getting, right? You're going to be starting off down here. Let's say this is the enthalpy of a liquid, and this is going to be the enthalpy of the vapor. They're going to have to meet together at the critical point, because at that point the liquid and vapor are identical, and that's why you have no heat of vaporization or entropy change of vaporization. And you should get something that looks, hopefully I'm getting this right, kind of something that looks like that. Wait a sec, no, that's not right. Is that right? This is the enthalpy. Enthalpy is a function of temperature. I might have the curvature wrong here. Because the heat capacity is the slope. This says that the heat capacity is decreasing. I think I got the curvature wrong. I have the solutions, I didn't remember the shape of it. I think it actually might be something like this, actually. No, it has to be linear. It has to be a linear, because that means if it's a constant heat capacity. Yeah, I think it looks like this. It has to look something like this. Right, because this is the heat capacity here, C sub P, and this would be C sub P. Heat capacity is a function of temperature. Always has to look something like this. Because as you increase the temperature, you have to have a higher, C sub P, this is temperature. You always have to have the heat capacity increasing because you're having access to more energy modes. One way to think about it is if you're, let's say you're a billionaire. If you're a billionaire, you can buy a yacht and you can buy a car, right? But if you're a compound or a molecule, if you can activate some high energy mode up here, well, yeah, of course you can still activate some energy mode down there, right? You've got lots of energy to go around, you can throw around. So a couple of things. For the enthalpy and the entropy of vaporization, the Clapeyron equation is going to be your gateway into assessing it. So in this case, you'll be looking at, from here you'll get dp dt, right? The change in pressure. Now this is the saturation pressure. So I'm not asking you to calculate the properties at all temperature and pressure conditions. I'm only asking you to calculate it at the saturation point. So for all of these, it's saturated liquid, saturated vapor properties for everything. Saturated liquid volume, saturated vapor volume. That's going to be your gateway into there. So really, once you've got an automated code to balance the fugacities out, this one's not too bad. The internal energy and enthalpy one, it took me a little bit to get. So a couple of notes on this one. For reference states, now I'm giving you a really healthy sort of introduction to this problem because I want you to all give it a really good shot because it's non-trivial. So for the reference states, I want them to be the internal energy of the liquid at the temperature of minus 50 degrees Celsius. That is equal to 0. Now, if I'm setting the reference state for internal energy, I can't also be setting the reference state for enthalpy, right? We get one energy reference state, one entropy reference state, but we can calculate that the H of the liquid at T equals minus 50 is equal to the U at the same condition plus PV, right? So that gives you a gateway name. And also that the entropy of the liquid at minus 50, now remember this is of course saturated liquid, that's why I'm only telling you the temperature, not the pressure. This is also going to be equal to 0. I didn't solve it starting this way. I solved it using a different reference state and then converted it just by shifting everything after the fact. Right? I actually chose a reference state that was, I don't know, I'll let you guys be creative at least on that one a little bit. But I didn't start it this way. I started it somewhere a little bit more straightforward. So to solve for all of the enthalpy and entropy values, you're going to be using the departure functions that you derived in homework 2. Meaning that you're going to have to couple ideal gas calculations with the departure function calculations to basically go from every temperature and then pressure, over here, going from every temperature of an ideal gas and then pressurizing it, right, to a vapor, that's the departure function, and then using the heat of vaporization to give you information on the liquid. Make sense? But this is a non-trivial amount of work. Conceptually, it's nothing new, But when you see it all put together, there's a lot of logistical challenges organizing it and keeping it all straightforward, right? Because it's just a lot of properties to calculate and making sure you're getting all of them right. You're not going to be assuming constant heat capacity, so you use the heat capacity information that's in the Sandler book. It says that it stops at 300. I just kept going to minus 50, and nothing bad seemed to happen. I mean, the van der Waals predictions are so bad in general, who cares? This is an exercise. But I even did it for the Peng-Robinson equation of state, and even with the extending the heat capacity range outside of the limits, it seemed to be pretty good. Well, maybe that's why my predictions were a little off. Okay. Questions on what is being asked of you. This isn't the only part. There's some other questions on there that test other concepts, but this is the bulk of the work. But you'll feel like $1 million if you get it done. Okay. So we'll do one, let's recap the Gibbs phase rule. Basically, we just have to tie up a few loose ends when it comes to multi-component systems, and then we can transition after the exam to talking about applications of multi-component, multi-phase systems, which is going to be vapor-liquid equilibrium, that's ideal, vapor-liquid, that's non-ideal, liquid-liquid, solid-liquid, and then chemical equilibrium. And so we're going to go into applications, but we got to clean up a little bit of things, talking about just the general theory of multi-component systems. Okay, so the Gibbs phase rule. So we have number of components, number of phases, and then degrees of freedom. So if I have one component and one phase, thermodynamics tells me how many variables do I need to define. Two. So remember, in thermo, we have the first law, which tells us about energy. We have the second law, which tells us about entropy. And then we live in a universe that has a finite, or we have a universe that has real space volume. So those are the three fundamental variables of thermodynamics. Meaning that if I have an equation, two of those are independent, and then the third one has to follow a relationship outlined by the first and second laws. So that's where we get 2 degrees of freedom for a single component, single phase system. All of thermo is built on this assumption as well, that we can fully describe a macroscopic fluid by 2 properties. Now, if I have one component with many phases, we showed earlier that our degrees of freedom are going to be 3 minus p. So if I have a 2-phase system, like liquid-vapor equilibrium, that means I only have 1 degree of freedom. Consequently, I only had to define one condition saying this is the saturated liquid internal energy. If I have 3 phases at the triple point, I have 0 degrees of freedom. I have no choice where the triple point is. It's just locked in place. Now, if we have many components, but only one phase, we have the 2 degrees of freedom that normally would be necessary to describe a single phase, plus C minus 1 additional relationships describing the composition. So for example, this could be like x1 plus x2 is equal to 1. Right? That's one additional, you have one equation for every 2, or you have minus 1 equation for each component. So this means that we would have C plus 1 degrees of freedom necessary for a multi-component single-phase system. What our goal is right now is if we have multiple components and multiple phases, can we fill in this table here? So we're going to take the same approach that we did previously when we derived Gibbs phase rule. So we're going to take the number of independent equations that we've got and minus the number of dependent, and that tells us basically how many variables we can control. So for every phase, we rationalize that we should have C plus 1. So that gives us the number of independent relationships. C plus 1 times by the number of phases. Now we have to deduce how many dependent relationships do we have, knowing that we have a system in multi-component, multi-phase equilibrium. So what is an example of a dependent relationship when we have phase equilibrium? What has to be equivalent across the phases?
Thermal equilibrium, mechanical equilibrium, chemical equilibrium.
Bingo, all three of those. So for thermal equilibrium, we have T of phase 1 equals T of phase 2 equals ... This gives us P minus 1 equations. For mechanical equilibrium, we have the same thing. Pressure 1 equals pressure 2 equals so on and so forth. Again, another P minus 1 equations. For chemical equilibrium, it's a little bit different this time. Now for a one-component system, we had that the Gibbs free energy of phase 1 was constant across all of the phases, giving us an additional P minus 1 equation. But for a multi-component system, we have issues. It's not the Gibbs free energy, it's the partial molar Gibbs free energy. So for species I, we have the partial Gibbs of species I in phase 1 has to be equal to the partial Gibbs of I in phase 2, which has to be equal to the partial Gibbs of I in phase 3, and so on. For component J, the partial Gibbs of J has to be equal across all of the phases. So this actually gives us C times P minus 1 equations. So here comes the really tricky part of multi-component, multi-phase equilibrium. If I have a system, we keep it simplified with just two phases. I need to make sure that the temperature is constant across all of the phases and the pressure is constant across all the phases. And I have to ensure that for every single component in the system, that I have the partial Gibbs free energy is constant across all of the phases as well. So we could think of a scenario that's not uncommon in, let's say, an oil field scenario. You could have an aqueous phase, right, because oil is almost always produced with water. You can have a vapor phase, right, where the light ends of the crude oil, the natural gases boil away, and you can have a liquid phase. Which means that for every single component in, let's say, crude oil, which could be millions of components, which you need to break down into pseudo-components, otherwise the math becomes intractable, we have to make sure that the partial Gibbs is constant for every component across oil phase, aqueous phase, vapor phase. Oil phase, aqueous phase, vapor phase. All of them have to be in equilibrium together. And all of these properties change as a function of temperature and pressure. So as the oil flows through a pipeline, let's say a subsea pipeline, which is really common in offshore production in the Gulf of Mexico, your temperature is going to be dropping as you flow the system down. Meaning, all of these are going to change as these change. And so it just becomes a very complex numerical mess. And that's why in our definitions of the partial Gibbs, right, or our definitions of the enthalpy, or even the definitions of the Gibbs, the mathematics become very complex, and so what we try and do is define the functions in a way that makes them the most useful and applicable. This becomes a very complex problem very quickly. Okay, so we've got our number of independent relationships here. We're going to minus out our dependent equations. So we have 2 times P minus 1. These correspond to our thermal and mechanical equilibrium. And then we have C times P minus 1. And if we go through the math and cancel everything out, we find a nice convenient relationship that most of everyone has probably seen before. the degrees of freedom is 2 plus c minus p, so number of phases. There, so we can erase this and say it's 2 plus the number of components minus the number of phases. That's how much information we would need to fully describe the system. Now, this just tells us the phase equilibrium, but it doesn't tell us how much of each phase we have. For that, we would need overall system properties in the same way that we talked about previously. We would need to know the overall system density, or the overall system internal energy, or the overall system entropy in order to figure out the quantity in each phase. Now, the Gibbs phase rule is very useful conceptually. Truth be told, in this class, you're probably not going to use it very much. It's more useful for someone like me when I'm trying to write problems to think about, am I giving them enough? Is this problem even possible to solve? But it's a fun little exercise, I think, as well. Especially in the grad thermal class, I really enjoy going through and seeing a lot of these relationships that are kind of just spit out at the undergraduate level, just kind of walking through and demonstrating that, how we got there. So that's why I kind of covered the Gibbs phase rule. All right. Next is the Gibbs-Duhem equation. This is still readable, or should I get a different marker? Still good? Yeah. So, we will describe what the Gibbs-Duhem equation is after we derive it. So just bear with me for a little moment here. Ultimately, we are going to do our standard thermodynamic derivation approach where we expand a variable using multiple different methods. So we're going to expand the total system property of something. This could be volume, Gibbs, Helmholtz, enthalpy, everything. We're going to do it two ways. One, with respect to temperature, pressure, and the composition. So changing all the different numbers of moles of all the different species. Then we'll do it with the product rule. Meaning that we'll just, derivative first times derivative second and vice versa. So let's expand whatever system property that we're talking about for a multi-component system with respect to temperature and pressure, meaning that we're going to take d of the system property with respect to temperature, holding pressure and the composition constant. And if we're holding the composition constant, then of course we can pull the number of moles out because that's being held constant in the system. Oops, dt plus. Do the same thing with respect to pressure, but hold the temperature and the number of moles constant. And then lastly, we're going to do the same thing with respect to composition. So we're going to have a number of terms here. Let's see. And again, we have this little obnoxious term here. We're holding the temperature, the pressure constant, and all of the number of moles for everything that is not I. So we're varying I. So if this is a three-component system, component A would be changing, but B and C would be held constant. Component B would be changing, but A and C would be held constant. That's the notation there. And then this is a function of this term right here. This is just the definition of the partial molar property of whatever the system that we're looking at. For these ones here, we can pull the total number of moles outside. Next, we're going to expand the same property, but in this case, we're just going to do it generally using the product rule. Well, hold on, I skipped a step. We're going to do one substitution here. We're just substituting. This is basically from the definition of the partial molar property. If we add up all the partial molar properties, it gives us the total system property. Everyone okay with that, what I did there? So then, that allows us to, oh, sorry, now that makes more sense, summation. Oh, let me do this better. Okay, there we go. I'm going to call this one equation A. I'll call this one equation B. So we're going to subtract A from B. And we get that 0 is equal to minus. This is what we call the generalized Gibbs-Duhem equation. Now the form that we were going to most typically see, and I will explain why we're doing all of this in 1 second. If we hold the temperature and pressure constant, which is of course the way that we would like to do mixing processes, so you don't have to worry, right, about how the system changes, system property changes with respect to temperature or pressure, right? So let's say, for example, we derived a deviation or departure function for the van der Waals equation of state. That was effectively looking at how do we change the enthalpy as a function of the pressure, meaning that we've got a real fluid that's not an ideal gas. And that was not too bad for a single component system. But the difficulty is that when you have a multi-component system, all of the properties change. And so keeping track of how all the properties change as we change the pressure or temperature, that's going to be non-trivial. Because the heat capacities of fluids change as you put them into mixtures as well. So, at constant temperature and pressure, we have two different forms of the Gibbs-Duhem equation. I mean, same thing actually. It's just one's in terms of mole fractions, one in terms of composition, or number of moles. Okay. What the Gibbs-Duhem equation is, it is a multi-component thermodynamic consistency relationship. That sounds like a mouthful. So this is a and it has a fair amount of, I guess, significance associated with it. Now, the Gibbs-Duhem equation is kind of like the, approach that we took here, or the triple product rule, or the chain rule. It's something that we're going to be using to derive expressions, not something that's going to be in a daily routine being applied, unless you're deriving sort of new approaches to solve particular problems. But what this is basically saying here is that, let's say I have a two-component system, an A-B mixture. That is saying that the mole fraction of A times by its partial molar property plus the mole fraction of B times by its partial molar property has to be equal to 0. Meaning that if I change the composition of the system, I have to be changing all of the other properties. If I change the partial molar property of A, I have to be changing the partial molar property of B. That tells me that if I have a multi-component mixture, I don't know who is causing the property changes, right? It's just the overall fluid property changes. So in the classic example of water and sulfuric acid, you mix the two of them together, it's an exothermic mixing process. And in that exothermic mixing process, a lot of energy is released. Now the reasoning behind that is because when you have your sulfuric acid, the hydrogens dissociate from the sulfate ion. This causes the water to form a complex around the sulfates and the hydrogen ions. Right? So is it really the sulfuric acid's fault for the energy release, or is it the water's fault for the energy release? Right? So ultimately, it's a combined total mixture property. Now, an analogy is mole fractions. Right? This is an analogy of what the Gibbs-Duhem equation means for mole fractions. So we know we have a consistency relationship where the mole fraction of species A plus the mole fraction of species B has to be equal to 1. Now this relationship must be true based on how we defined the mole fraction. The mole fraction of A is equal to the total number of moles of A divided by the total number of moles in the system, which is A plus B. Likewise, the mole fraction of B is defined in a particular way as well. Same reason that how we define partial molar properties, since we defined the partial molar property the way that we did, we have to have this consistency relationship, meaning that we cannot independently vary the properties of fluids in a mixture. So if I wanted to have the mole fraction of A increase, I could accomplish this task by either increasing the number of moles of A or by decreasing the number of moles of B. So I cannot tell independently, if I know that the mole fraction is changing, which of these two processes occurred. The Gibbs-Duhem equation is the very complicated multi-component thermodynamic equivalent of that concept. So it comes up in derivations to simplify expressions to get a little bit more straightforward. Now, the form of the Gibbs-Duhem equation that I have listed right there is by no means useful whatsoever. I mean, maybe in a derivation, but effectively this equation here tells me that I'm trying to independently vary the partial molar property, which is not trivial. I would like to independently vary composition or temperature or pressure, right? The same way that when we defined the first and second laws of thermodynamics, they were properties of ds, du, and dv, which are not trivial things to vary. So what we need to do is we need to manipulate this expression to get it into a form that is actually useful. Thankfully, the derivation is highly unpleasant, so we're just going to skip over it and go straight to the conclusion. So the starting point is again going to be like, so what we're going to try and do here is We're trying to convert the dependency on the partial molar property to a dependency on something that is actually a variable we can control in the lab. So what we're going to do, I'll just start the idea or thought process. We're going to expand any partial molar property with respect to temperature, pressure, and mole fraction. So from here, we're going to have a whole bunch of, this is going to be our partial derivative, a summation of a bunch of partial derivatives. And then we're going to take this term and plug it into here, and then plug it up here, and then do a whole lot of tinkering and algebra and working things around. And we get the final result, and even the final result is, I would say, unpleasant. So a lot of the terms cancel out, and the result is this equation. Double summation. And I'll put useful in quotation marks here. And by useful, meaning that it's dependent on a variable that we can actually control, which is the mole fraction. But this is a double summation, so we're first summing with I, then with j to number of components, then the number of components minus 1, and it's a little bit of fun. So let's just go through really quickly for a two-component system. So if C equals 2, that means that this equation here will be equal to, so first we start off with I as being 1. So that's x of 1. Okay, got that part done. Now j is starting off at 1 as well. And we're only counting this one to c minus 1. So that's going to be d theta over bar of 1 dx1 at constant temperature and pressure. Okay. Now we're not going anymore because j is 1, c minus 1 is 1. Now we're going to go to I equals 2. That's x2. And again, we're starting off j equals 1, so that's d theta of 1, d, that's j x1, x1. Oh no, sorry, that's I on the top, too. Oh, sorry, I missed this part here. This one. dx1, dx1. But those end up canceling out. For a two-component system, they cancel out. So the form that we're going to find most often for the Gibbs-Duhem equation in derivations is this one here. Now in your minds, just remember that this is just like one of the tools that we developed, the triple product rule, the chain rule, that allowed us to manipulate the combined first and second law, which allowed us to get from dependencies on U, S, and V to dependencies on temperature, pressure, and specific volume. So it allowed us to actually interact with the thermodynamic world through the world that we like to work in. So this is really just kind of a mathematical tool for us to help better derive different systems. All right, so don't have a ton of time left. I don't know if we can get through all of this here. Let me generally talk about, so on Monday we'll cover the content necessary to solve the last problem on the homework, but I'll introduce a concept for mixture properties. So one thing in the Gibbs-Duhem equation that's kind of apparent here is that the slope of how a mixture property changes with respect to the composition is very important. So slopes and curvature in thermodynamics is very important, right? Same thing as in mass transfer too, right? Let's say, for example, you're having diffusion away from a surface, right? There's a big difference between this and that, right? At the interface here, let's say this is x equals 0 for, let's say, a mass diffusive flux. These have very different fluxes, right? The flux is related to the gradient, if this is concentration here, or temperature. Which of these two lines, A or B, has greater flux away from the wall? You say A. Why do you say A has a greater flux away from the wall? Why?
Slopes deeper.
What's the flux of B?
0.
Yeah, there's no flux away from the wall in the B case. So if this is, let's say, a hot plate, and this x is the distance away from the hot plate surface, which of these two is a better representation of the temperature profile? Oof, qualifying exam, guys, it's gonna be rough. This is 100% the type of questions you get asked. But you haven't had transport yet this semester, or this year, right? This has the greatest flux, right? Because there's actually a finite slope. The flux is proportional to the gradient in the system. And for system B, there is no gradient, it's flat. It means there's no flux. So this would be effectively an insulator, which doesn't make any sense. Right? So the endpoints are both locked in the same position here. But this one has real physics associated with it. This one here does not. So curvature is very important. In thermodynamics especially so, because of stability criteria of entropy. Entropy has to have a certain curvature. So when it comes to mixture properties, so if I have some property that I'm measuring here. Now recall, the ideal mixing characteristics right, this would be our ideal mixing. And this would just be a summation of the mole fraction times by the pure species properties, right? A weighted average. Now this type of relationship is only going to be appropriate for things that don't have entropy, so just keep that in mind. This is non-entropy related events. And this is the real system, which is a weighted average of the partial molar properties. So the difference between these two lines is the change of the property during mixing, which is the difference between the partial and the pure species property. So let's say I'm doing density measurements or calorimetry. I'm doing real measurements because I want to calculate partial properties in order for me to better estimate phase equilibrium. So instead, what I'm going to be looking at, potentially, is I want to look at the change in mixing properties here. Now, if I represent this set of measurements here, this could be, for example, let's say this is specific volume or, reciprocal of density. So what I'm doing is I have a densitometer or a pycnometer, right, where I put the fluid in the densitometer. It either is a U-shaped, vibrates, blah, 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 gives me a number, right? I plot it out. I can do a weighted average, assuming ideal mixing. So if I were to plot out the change of volume in mixing, in this case it may look something like that, right? But I have numerical uncertainty in my measurements. So my line isn't going to look exactly like this. It's going to be bouncing around. And this is potentially very good measurements, right? Where the noise is random. Now, if I wanted to go ahead and calculate property changes here, there's potentially going to be some complications. Because taking derivatives of numerical data is generally a bad thing to do. Because uncertainties get magnified when you take derivatives of properties. Uncertainties get minimized when you take integrals. So who is familiar with numerical differentiation and integration, like quadrature or that's numerical integration. Triangle rule, trapezoid rule, right? So to approximate the slope, you connect the dots, measure the slope, connect the dots, measure the slope, connect the dots, measure the slope, right? Well, here's a big problem. If I were to then look at my plot would look something like this, which is probably not good, considering changes in slope can potentially be big deals in thermodynamics. So what we need to do is instead find a way to fit the data with a smooth function that allows us to then differentiate that smooth function that we can then use to plug into subsequent thermodynamic relationships. Now, the application of this will become more clear when we actually talk about measuring partial molar properties, which is what we did not quite have time for, but we'll talk about that on Monday. So, the problem when you differentiate something, it increases the noise. The solution that seems to be the best appropriate fit with a function, then take the partial derivative of that function itself. One that is very commonly used is to fit property changes of mixing is the Redlich-Kister. Redlich-Kister polynomial. It looks like this: x1, x2. So the idea here is that we fit it with a smooth polynomial that is not going to give us weird characteristics and changes in slopes very suddenly or drastically. Now, this particular form is very convenient because it has limiting cases. For a pure species, there can be no property changes of mixing because it's just the pure species itself. So this polynomial, anytime you have a 0 of either mole fraction of component 1 or mole fraction of component 2, which is anchoring your two endpoints, everything has to equal 0. So that's why it's a good functional form for that kind of characteristic. Now, the whole point of all this is that actually these are the measurements that we make in order to measure partial molar properties. And so I skipped over one strategy of doing so, but we'll talk about that on Monday, so it'll become a little bit more clear why we have to bother taking derivatives of this data in the first place. But you can see in the Gibbs-Duhem, it pops up quite a lot, changes in properties. Okay, so, question? Yeah.
The polynomial we choose to fit the delta of mixing, delta zeta of mixing, should satisfy the Gibbs-Duhem equation, right?
One more time?
The polynomial or the function we choose to fit the delta zeta of mixing should follow the Gibbs-Duhem equation.
It should have to, yes. So the Gibbs-Duhem should never be violated. So one of the ways you can use the Gibbs-Duhem is to verify if your thermodynamic calculations are accurate. So for any property, any measurement you make, you should be able to calculate these values and they should cancel each other out. If not, there's a problem. Now, one area where this comes up a reasonable amount is in activity coefficients. Activity coefficients are related to the Gibbs free energy of mixing. And so if you know the activity coefficient of one species, you can use the Gibbs-Duhem to calculate the activity coefficient of the other species. So that's one area where it comes up a lot. But yeah, that equation can be used to validate data. So everything that you throw and try and use and model for a multi-component system has to follow Gibbs-Duhem equation. All right, so please take a look at the homework. I'll be back like normal on Monday, ready to answer any questions. So yeah, take a look. See ya.